All right, welcome back, everybody. Sorry to miss the class on Wednesday. It was this security conference called NESS. It was in San Diego. And I hope that the presentations went well and all. So today, as I said, this is going to be our last module. We're gonna talk about trusted execution environments. The plan is hopefully I'll cover most of it today, and I might talk a little bit about their project force as well, because there were some questions. Although I said no, but I changed my mind. Then on Wednesday we're gonna do our final paper presentations, and I'm gonna also talk a little bit about your exam for the next Friday, the next Wednesday of next week. And then whatever remains of module 10, I'll cover it on Wednesday as well. And then next Monday, gonna be mainly just reviewing different topics and kind of like, giving you a few more pointers of other things that we didn't discuss. Although whatever we say on Monday next week won't be part of your exam. And then of course, Wednesday would be just the exam, and then that's it. In terms of the project, so CA4 is due, I think, 10th. And then we're gonna have like a one final like blockchain based. That one is simpler, easier to do. Is anybody has already done CA4 finished? Okay, there are a few. Nice. All right. Is there any questions before we get started? All right. So last time we talked about attestation, right? Like we talked about checking and making sure that the system works. And then if you kind of like remember, we like talked about the story of how do we build systems, right? And we kind of took a long journey of various different things and looking at various different possible attacks. We initially talked about like how do we actually build system security by design using principles. Then we used the idea of secure boot and trusted platform modules, TPMs, and said, okay, at least the least we can do is making sure that the system is properly boots. And we follow some kind of rules in order to make sure the system is secure. Then we kind of like start all these kind of various different types of attacks. We start with sensors, and show that sensors are actually like one of the biggest issue in our systems. Then we talked about kind of like faults, right? And then we go through like saying that, okay, not only there are these problems, there's also kind of effect of computing on the outside world. And then we talked about side channel attacks, right? And that was kind of like more of like external problems to our systems. Then we go look at the internal problems and say that, okay, the system works correctly, but as we kind of like work with the sensors and inputs, then we're going to have a bunch of different memory safety problems, right? Safety and corruption problems. And then we show that essentially these languages that you're using are not secure languages. As a result, there might be temporal, spatial misuse of various different pointers in our system. And an attacker can actually use this in order to change data, in order to change code, or even both. And then they can either like attack, integrity of our system, or even worse, they can do some form of hijacking of the control flow and so on, and actually do something malicious there. But then we kind of spend a decent amount of time talking about different malware, how we detect these kind of attacks, how to fix them, and so on and so forth. And then kind of like last thing that we talked about last time was, okay, let's forget about kind of preventing this. Let's talk about detecting this, right? And that's where the idea of like attestation came into the play. And then we saw the challenges of different attestations. And then hopefully once you're doing your computer assignments, you learn a little bit more about that. But then the last thing I want to talk about, of course, there are like multiple different things, and there are like deeper things that we need to talk about that we didn't. But at least to kind of finish this story, I want to talk about this last bit, and that is like, let's assume that we securely boot our system and we have the we have our designs kind of like fully started up and being used, but then there are a whole bunch of these bugs, right? And this attacks that could compromise our software and more importantly our operating system. That's like a big deal for us, right? So now the question is, can we actually do something even if we are living in this compromised world of trustworthy world? Can we kind of salvage something out of this? That assuming that the system could be compromised, can I still do something useful with the system, right? And this is where the idea of trusted execution environments comes into play. That essentially the idea is that, we started with something good, and that was TPM, right? And then we said that, okay, as long as we trust the manufacturer and we kind of adhere to some form of standards and so on and so forth, we can say that TPM works correctly. But TPM was kind of like a one-time thing that's kind of passively store some secret for us. And then when we want to boot the system, is kind of like booting the system correctly. It never goes beyond just booting the system, right? So what we want to do is that being able to use that TPM actively, dynamically through the runtime, such that this is kind of is our sanctuary, right? So like, if my entire system is kind of compromised, I still have kind of like a small area that I can communicate from external world, and I can run these things. Even though this part is kind of compromised completely, I still can find, like, design some hardware that's kind of, it's completely independent. It's kind of like thinking about like an island that is like being managed by itself, and then regardless of what is happening on the rest of this system, this can always like work correctly. And then if you think about this, then you will see that essentially we need to kind of have hardware changes in order to kind of facilitate this isolation and making sure that like this part that is compromised cannot really mess up with us. And then, of course, we need to have kind of a software layer on top of it, because hardware alone doesn't solve this problem. This needs to talk to the outside world. This still needs some form of scheduling and services and so on and so forth. So I need some form of operating system or some thin layer of operating system that can manage this. And then, of course, as I said, since the original operating system is compromised, this has to be kind of a separate operating system. And I'm going to talk about what is the difference between these two. So in general, this is kind of like the basic idea of what we call the trusted execution environments, or TEEs. And the idea has been around for longest time. It's like introduced in early 2000, but it's been commercially used since the beginning of ARM Trust Zone. This is actually something that's very commonly used in many ARM devices. And we're going to actually talk about that. And then other companies, including Intel and so on, they have their own version of TEEs, including what they call Inter-Software Guide Execution, or SGX. And AMD has its own called SEV. And RISC-V has its own called Keystone, and so on and so forth. So it's kind of now it's the standard across the industry. Almost all the major manufacturer has some form of TEE. Not all the processors have TEEs, but many processors do have TEEs. And since we are still talking about IoT devices and edge devices, we are mainly working on ARM-based cores, right? And then TrustZone is actually the common thing. There is actually very it's available in many different instances of an ARM core, so it's not like something unique. And then actually ARM recently is designing a new version of TrustZone called CCA, Confidential Computing Architecture, which is kind of the glorified version of T, which we're going to talk a little bit about that as well. So first of all, the question is like, how come that if you're kind of like, if you're having this system compromised, why this system cannot be compromised, right? This is a basic question of like, it seems that I'm kind of reinventing the entire system and saying that, okay, magically this red part on the right cannot be compromised, this part cannot be compromised, but this part can. So why? The reason for this is kind of based on this important things, is that the trusted execution part is very small, okay? We usually call that trusted computing base, trusted, or TCB, trusted computing base. So this TCB, this part that we trust, should be very small. The reason that it should be small is that because then you can verify it either manually or using all these tools that we talked about in the class and so on. But when it goes to the larger code, this is a much harder problem. Why? Because we talked about this, about coverage, basic blocks, finding the inputs and all those things. When we're talking about 1,000 lines of code, it's doable. But when we're talking about millions of lines of code, then it would be very, very hard problem to solve, right? So this is all about how easy it is for us to fix something. So generally, if something is small, we can check it easier, but it still doesn't mean that there is no chance of having any problem. Okay, so still there might be bugs, for example, in the TCP of these kind of high-end systems, but the chances that you find a bug in something very, very small significantly lower than something that's very, very large. Okay, so this is kind of like the basic idea of why the trusted execution environments are generally much safer and much more secure than a traditional like a Linux, Ubuntu, or generally any sort of big kernel like Microsoft, Windows, and so on and so forth. Okay, that's kind of like the idea. That's kind of like I wanted to kind of get that out of the way. Well, let's actually talk about how do we design this. Okay, so the main ingredients, of course, are hardware changes and the software changes. And then this, this area of trusted execution environments is really depends on different goals and objectives, and also depends on the manufacturers and how they approach this. In this lecture, I'm going to kind of give you a bunch of different examples of industry examples and some academia papers. So you will see that kind of part of it is repetitive. So you see that basically they mostly all of them using similar principles. So part of the slides would be kind of repetitive of the same thing over and over, but there are parts that are like slightly different from one to another, depending on the need and so on and so forth. Okay, but in both cases, kind of like you need some hardware changes and you need some software changes. Yes.
I didn't understand the takeaway from the previous slide. So what is the conclusion? That is the answer to why can't we fix larger codes? Because I imagine that we can just extend the same principle of like making the TCP bigger, and it would just be like more time consuming for the developer or hardware designer. Or is there like more fundamental reason or theoretical reasons why we can't fix larger codes?
So the theoretical reason is like the basics of probability, right? So if there are, let's say, there's equal chance of having a bug based on number of line of code. Okay, so let's say, just say that historically for every 100 lines of code, there is X% chance of having a bug. Okay, so now if I tell you that I have 100 N lines of code, depending on how large this N is, this X becomes bigger and bigger. Right, so that's kind of like the probability of finding, N, with like making this N larger and larger means that the probability of having a bug in the system is going higher and higher. Okay, so it's just, again, there's nothing fundamentally preventing us from not having a bug at all in a millions line of code. You technically can. You can write a code. But it's just historically, we never been successful of like writing million lines of code and not having a bug. Okay, it's just the chances of something can go wrong will go wrong kind of thing. Make sense?
Yeah.
All right. So so as I was saying, so you're gonna see some hardware changes and some software changes. In some cases, people were interested at not having hardware changes and just software changes. A kind of similar flavor to the previous works that we looked at in this class as well. Generally, for software changes, the main thing that we are adding is a new paradigm which we usually call enclaves. So think about enclaves as this kind of self-contained unit of software that can run arbitrary software. Okay, that we can run things there. And the main thing about enclaves is that they are different than normal world applications. Okay, so they're kind of like they're secure, backed by whatever T we have. So the T is kind of providing this basic block, which we call enclave, and then each of these enclaves are an independent software. Okay, and then of course to kind of manage this enclaves, because you usually don't have just one, you have multiple enclaves, you need some form of kind of management system software, right? And you may call that a runtime or an operating system or a firmware, depending on like again the application. There could be different names for it. Okay, and then of course these enclaves usually needs to still talk to different other components. They need to talk to the hardware, to the memory, the IOs, to the outside world. So again, the system software is responsible for managing that as well. Okay, so two things that we are introducing. One is enclave, which is this basic blocks, this software, this application layer thing that is controlled by the T and is different than our normal applications because now these are secure, they're not controlled by the normal operating system. And the second thing is that we need to add some form of system software to kind of manage this. And then again, this system software is different than the normal operating system. This is something small, preferably, right? So that we can kind of verify it before actually using it, okay? On the hardware side, we need to essentially have hardware capabilities to achieve this goals in software. The main thing is that we need to provide isolation, okay? We need to provide isolation between regular application and regular OS and these enclaves and this system software for the enclaves, okay? So essentially, mainly we need, and then this is mainly for memory and IO, right? Because execution, you can always like use the same course. It's just accessing memory and accessing IO should be managed by hardware, and we should ensure that there is some form of isolation between this untrustworthy part of our system, which is the normal operating system, and whatever application that's running on top of it, and this kind of trusted execution environments and their applications, okay? So usually we kind of, ARM is using this terminology called secure world and normal world. So you can think about this is our normal world and this is our secure world. And then there is, as I said, in this secure world, we have kind of a system software, and then we have a bunch of applications on top of it. And then in this normal world, we have the same. The main thing is that, for example, if there is something that we need to access to the memory or the IO, hardware should be able to kind of distinguish the request that comes from the normal world versus the request that comes from the secure world, right? So this is usually what we need to do. And then additional things could be added on this system. For example, we talked about things like side channels. We talked about fault attacks and so on and so forth. We might say that, okay, now that we are kind of fixing this secure world and normal world, maybe we make this secure world even more secure. Maybe make it more robust against, let's say, side channel attacks as well. Okay, although we cannot, for example, fix side channels for the entire system, maybe I can fix the side channels for the trusted execution environment applications. Okay, so this is kind of like additional things that we might do in order to fix this, make our systems more secure. Okay, and then this is again the picture of kind of a complex way of thinking about software changes. As I said, you can see various different types of applications in the system. Okay, so first of all, this part is the untrusted world. This was what we normally had in a system. Okay, so this is like what we have in a regular computing system was this part, right? So you have a bunch of different apps, you have your operating system, and usually operating system is kind of like controlled by some hardware, okay? So what we are now adding is this part on the right that, as you can see, you can have a bunch of different enclaves, and each enclave usually has their own kind of runtime environment or operating system as well. And we usually again, this is, I think, the terminology that I borrowed from RISC-V and Keystone. So they call it enclave apps or e-apps. Some other works call it different things. So just don't worry about the names, okay? And then as a result, as you can see here, usually, if you remember, I told you that we have, different privilege levels when we are designing our systems. We have like a user level and privilege level, or you can call it a machine level supervised model and so on. This is again terminology of RISC-V architecture. So in order to kind of distinguish between the normal world and the secure world, we need to definitely have additional layer that's kind of oversee these two operating system levels, and we usually call that a machine model or security machine. That is, this is even beyond the operating system, because this is the one that's kind of like, this is our root of trust in some sense, right? This is the one that's going to ensure that our system is secured. It loads the operating system, it loads all these other enclaves, and then it kind of manages these things, right? So it's kind of one layer on top of all the other layers that we have. Yeah.
Why can't the security model be compromised?
Say it again.
Why can't the security model be compromised?
So the question is why this SM cannot be compromised, and that's a good question. It can be, first of all, so there are attacks. But the thing is that, first of all, this is usually just purely hardware. It's not really like active, kind of like interacting with the physical world. The second thing is, as I said, this is very small. So usually you can actually, for example, check that there is no obvious buffer overflow in the system, right? But doesn't mean that, again, none of these things says that there is like a silver bullet, kind of like, it's completely bulletproof. Nothing on this enclave world can be attacked and so on. Then that's a story for a different day of like how you attack this. But at least it's an improvement over this kind of very, very untrusty world. Yeah.
What would be an example of a enclave app? Or like,
The question is, what's the example of enclave? It could be anything. So let's say, for example, you have an application that you're worried about that might be vulnerable to any sort of attacks. You'll run it on an enclave. There is a trade-off between enclave and normal, as we can explain. But generally, let's say that a remote user wants to run something on the device. They don't have any idea whether this is going to be used or not, like whether this system is compromised or not. They can provide this for them in that case. So it's more of like, if you have something to worry about, if you have like some data that you worry that is going to be compromised, then it's probably a good idea to run it on the secure one. Yeah.
So you run like those critical apps on the enclaves, and then the security monitor is just monitoring whether the enclaves have been compromised, or
I'm going to talk about what is happening. No, the security monitor just makes sure that this OS and this runtimes are being loaded correctly.
oh,
Okay. But then this is itself is self-contained. So it's actually like, as long as you have the isolation in the hardware side and the software side is not compromised, then you're good to go, right? Because, for example, if even here, for example, something is compromised here, okay? If they're trying to, for example, change memory of this app, they cannot, because we have proper hardware isolation that doesn't allow access to these. And then again, there is no, assuming that there is no bugs here, then even if this app kind of talks to the outside world, the outside world cannot compromise this because there is no bugs in this system. But again, for example, this enclave apps are vulnerable to the same sensor attacks that we discussed a long time ago. Okay, there's nothing changing this format of the system, right? Or for example, they're usually vulnerable to the same fault attacks or even side channel attacks. But as I said, these are additional things that now we can add on top of this. This is kind of like, think about this like an economy and premium kind of version of applications, right? The normal applications are economy applications, and then premium versions goes to the team. So to kind of like summarize the software changes, the SM or security monitor is the ones that's kind of like, controlling everything. And this is part of our trusted computing base, TCB. And as I said, each application usually needs some interface to interact with the rest of the world. This is usually what we call runtime environment, or as I said, sometimes it's even called a full operating system. But the most important thing is that they're usually much, much smaller than a regular operating system. And then the important thing is that you might have multiple enclaves. And again, here, depending on the design, these enclaves might share things or might be completely independent from each other. For example, in trust zone, ARM trust zone, you can have multiple enclaves, but they are not different physical entities. They're just part of the same thing. So essentially, all of your sensitive applications are in the same pool. In other words, they need to trust each other. Okay. But for example, the SGX model in Intel is assuming that they are separate things. So essentially, you can have many, many different independent applications. And the newer ARM CCA version, as I said, this one is going to be also kind of this new format of like things are actually mutually distrusted. Okay. On the hardware side, as I said, we need the capability of hardware isolation. In order to understand how does it work, I mean, the simplest things you can think about is some form of registers that kind of force who can access what, okay? So for example, let's say we have a bunch of these, physical memory management or memory protection registers. And then each one, for example, usually have some form of configuration and some address ranges. That's, for example, say that, okay, this enclave app is only has like, for example, this part of the memory access, this part of the memory access, and this part of security monitor access. Maybe it doesn't have access to the others, and so on and so forth. So for example, we can say that something is readable or writable or not writable, and so on and so forth. And depending on different contributions, then you can enforce any sort of sharing, any sort of writability, and so on and so forth. The important things I want to show you here is that you can have multiple of these registers, and these are not infinite number of registers. Of course, there's like finite number, but what this kind of propose and achieves is that one can share things as much as they want. Okay. Yeah.
So how is this, the next one different from the negative stage?
The left one is different. So I think the right one is for E1, for the enclave one. So enclave one, for example, says that you can write onto this region and this regions and nothing else. The non-secure one cannot write to E1, E2, or SM, can only write into this white sections. Okay, so think about like this white section is the parts that I can write to. This gray parts is the parts that I cannot write to. Okay, so for example, this picture is trying to show you that regular applications cannot write anything to E1, E2, or SM, obviously, versus E1 can, for example, write to its own area, and then maybe there is some shared area somewhere that it can also write. All right, so this is kind of like hardware and software changes. Again, like once we give you a more concrete examples, you will see the actual changes, but this is it's one of the possibilities, okay? And the final things before jumping into the example is how do we even load the program? And the thing here is that, again, the operating system itself is not trusted, okay? As a result, any sort of communication with outside world needs to be kind of securely managed, okay? Typically, we use encryption, and for encryption, we need keys. And another thing that we don't trust is that we're not really sure what's going on that remote hardware, right? So everything we do, we need to first check, okay? So for example, let's assume that you have a remote user. So this is the user, and this is the hardware that we want to talk to, okay? This is SGX terminology here, but again, this is very similar to all of those. So I've just borrowed this from the SGX, but just keep in mind that, the names are slightly different, okay? So what we have on this hardware is basically we have this attestation key, okay? This key that is kind of burned into this trusted platform, okay? And then let's say, for example, we want to create a new enclave, okay? This usually we call this, secure container or secure enclave. So we create this enclave. This is a new app the new process that we generate, okay? So now this user wants to communicate with this secure enclave, okay? And anything else in this system is not trusted. So the goal here is that this user wants to send some data. Optionally, they want to send some code, and wants the secure enclave to run that code, and then eventually they want to get the results back, right? This is kind of the goal, right? You're talking to some untrustworthy thing, there is a trustworthy parts within that untrustworthy systems. How do I kind of tunnel through that untrustworthy system, okay? This is how we start. Of course, the first thing that, the user and the hardware needs to agree upon is some form of a key, okay? Because you might create lots of these enclaves, and you don't have key for each one, right? So as you create the enclave, you need to kind of create a new key within it, okay? So how do we do that? We usually follow some form of key exchange algorithms. If you're not that much familiar with key exchange algorithms, I suggest you to look at Diffie-Hellman key exchange. The basic idea is that I create some form of a random number like A, and then I create this G of A, I send this G of A. And first of all, as you can see, each container itself has some initial code and data, right? So it's kind of like the libraries and use and so on. So this is basically this public code and data. This is the initial state of that of that enclave. Okay, so now what we are having here is that we send GA to the enclave. Enclave will create this B, and then it's gonna like send create this G to the power of A and B, and then this would be basically the shared key. And then they're gonna send this G of B to the user, and this way both of them are gonna agree on this key. Again, how the key exchange works, that's a separate story. I don't want to get into it, but generally just accept it from me that if we follow this protocol, we're gonna eventually find a key between them. Okay, so after this kind of initial kind of key exchanging that we both of them now agrees on some keys, now it's time to kind of do verification on the enclave side, proving to the remote user that we are indeed should be trusted. We are indeed an enclave. Sure. How do we do that? We do that classic remote attestation that we talked about. Okay. So we essentially compute a hash over our own content of memory. And then we sign this using the key. Okay. Using the attestation key. And we send that over to the remote user. The remote user knows this correct state here, knows this M because this is public code and data. Okay, so it knows that this should be the correct hash. It also knows that the attestation key of this particular hardware, because this is hardware dependent. For example, for SGX, Intel has a database of all the attestation keys of every single hardware that you need. So you can always go and kind of check it. And usually this is public private. So you never share the private, you usually only share the public side. But if you remember, digital signatures, we said that you sign with your private and then check with your public. So that's kind of the idea. But anyway, one way or another, the enclave they're gonna compute the hash, sign it, and then send it. The remote user gonna check this M, and then it's gonna trust this device if this M is the same as the M that they're expecting. Then this is now the time for the remote user to send their actual code and data. So they're going to encrypt it using this new key that they kind of agreed upon. They send their secret code and data. And now the enclave has this initial data, has the secret code and data. So it can now start executing this program. It starts executing that. At some point, it gets to results. Once it wants to send the results, again, it's going to encrypt this result. And then send the encrypted version of results. And then the remote user going to get this result decrypted with the key and then have the final results. Okay, this is kind of like the life cycle of this. The important thing is that in all these processes, you can see nothing leaves this enclave without being encrypted, right? So in that case, the operating system on that hardware never sees data unencrypted, and then any attempt of accessing the data will be blocked by hardware. On the other hand, the remote user also knows that this system can be trusted because we have the keys, the attestation key, and then usually follow this remote attestation protocol. Does that make sense? Yeah.
Can the untrusted section, let's say it's compromised, just not comply with any of these? Like,
yeah, so you can always have denial of service. So for example, you can completely kind of shut down the system so that you can never create an enclave on that device, right? Or if the request comes, you kind of not forward it to the enclave. So this is just making sure that, you know, integrity and confidentiality are satisfied. It doesn't say anything about availability.
No.
Yeah.
Attestation key is said in the publicly known key.
Say it again.
Attestation key is publicly known.
So what I'm showing here is that attestation key usually is a pair key, so it has a secret and public. The public everybody knows, the secret nobody knows. But again, you can actually have attestation key. You can have a symmetric attestation key if you want to. The only problem with that is that you have to store this symmetric key somewhere. Any other questions? Okay. All right, so let's actually talk about example. So as I said, the most important one, especially for IoT devices, ARM trust zone. ARM trust zone is basically the fundamental idea in ARM trust zone is having two words. Okay, the normal word and the secure word or trusted word. Okay, the normal word also called rich execution environment. That's why they call it RE. And the secure word is also called trusted, so that's why it's called T. So you have RE and T, okay, or normal word or secure word, okay. So the idea of trust zone is that the trusted part can obviously access anything on the normal part, but not the other way around. And then another important thing is that within the trusted word, everything is trusted. So it's kind of really just two modes, either trusted or not trusted. There's nothing in between, okay? So it's not like some apps can trust some others, but some others don't, and so on and so forth. It's just two. And then another reason that we use this word rich is that our normal word is just our normal word, right? It's like a regular computers with all these different kind of complex operating systems and so on and so forth. So that's why it's very rich. It's very capable. The trusted part should be as small and as compact as possible. That's why it's not as potentially as rich. Okay, this is kind of like if you think about the design is how it works. The apps on the normal world has this rich OS, and the secure world has its own secure OS, and then you have this trusted apps. And if you remember, there's like a layer beneath this that's kind of like manage everything. That ARM usually call it secure monitor or SM. Okay. So the implementations on the hardware side, there are kind of two main things that kind of enable trust zone. There's this the access bus control. It's based on this AXI protocol. For those of you who don't know what is an AXI, this is just a protocol for sending and receiving different IOs together. Essentially, the idea is that ARM just basically says that the only thing that we need to add to the system is just one extra bit for every memory transaction, okay? That bit is either 0 or 1. 0 means not secure and 1 means secure, or other way around, okay? So whenever we want to allow access things, we're going to check whether this request is coming from the secure word or coming from the normal word. And if it's trying to read a bit 1 or bit 0, okay? If it's secure and try to read something secure, then we let it read. If it's secure but it's coming from a non-secure word, then of course we have to block. Okay, very simple kind of access policy of just one bit, and this one bit is kind of appended all the way through the memory. Okay, so every access is just basically by that one bit. And then in order to kind of run things, then you need to do time slicing. Okay, so if you, for example, there are multiple things that you need to kind of run, like if you have just one core and then you have a bunch of secure apps and some normal world apps, how do you run this through this kind of like one core is that you need to context switch. Okay, so you need to run normal applications, then some secure applications. But of course, you cannot just regularly context switch. You need to context switch it securely. Okay, that's why we usually go through what we call, go through the monitor mode for context switching. So if I go back to this picture, if I, for example, run this application here, okay, I run it on this core, and now I want to run this application using this operating system. And let's say I have just one physical core, okay? So the way I do it is that I run this application, and now at some point I decided that I need to run this application. So this rich operating system needs to context switch to this secure operating system. This context switch has to go through the secure monitor. So rich OS sends a request to the secure monitor. The secure monitor going to do the kind of cleanup if necessary, and then jumps into the secure OS. And then again, once we are done with running this app, we need to go back and switch to the secure monitor and then switch to the rich OS. So it's kind of like, a switch back and forth between secure and normal. That's why there is an associated overhead in terms of runtime whenever you're switching between normal and secure. So it's not like a great idea to constantly switch between them. But sometimes you have an application that has both sensitive part and non-sensitive part. So you need to kind of constantly switch between these two. But just keep in mind that this switching needs to go through the secure monitor, which has some overheads. Questions?
Is there like a priority where, let's say, secure app wants to get some resources and the non-secure is using it? Like,
Yeah.
do they immediately switch context?
That's a great question. So this again goes back to that availability question. That is, let's say if these apps are trying to compete for resources, what should we do? So the default version of Trust Zone doesn't really kind of understand the differences. So it's usually just follow whatever scheduling algorithm that it follows. So most of these are kind of some form of first come, first serve, round robin, things like that. But again, the question might becomes that, oh, what if one app is maliciously trying to kind of let's hog all the resources? What happens? In most cases, as I said, systems don't understand to kind of circumvent the soup. But there are lots of works on availability for trusted execution. And those works are actually like being able to do this. And then, yeah, there basically the security monitor needs to be extended such that it understand the passage of time, the criticality of different applications and so on, so that it can actually support this. But this is actually very, very new kind of concept. Yeah.
But you said in the last slide, REs cannot access the trusted one thing.
Yeah, so RE cannot access trusted one. That's why I'm saying the secure monitor is the one that knows what's going on. Because secure monitor has complete understanding of access patterns of rich and access pattern of the trusted. So if, for example, say that, okay, oh, there is a request coming from this side, I can pause the rich and then let this go, right? So
But you said, suppose there is only one code, then RE can use the code which is given to secure OS. So that way, doesn't it negate and contradict the point?
no, so that's why you switch. So RE can talk to SM, okay? So RE, let's say you have two different applications, okay? Kind of like this, and let's say this is time. Okay, this is, for example, let's say this is a regular application. So what happens is that once it's done, at this point we send the request to this SM. The SM kind of gives the control to the T, and then the T takes over and then starts running its application. Okay, and then again, once it's finished, the same process goes to the SM. SM goes to RE, and RE kind of takes over. Does that make sense? And then in terms of booting, I'm not sure if I say this here, but essentially we boot first into SM, then we boot into secure ward, and then we switch to the normal ward. Okay, that's usually the way, because this is kind of like the steps, right? So the SM, then RT, and then our RE, right? And then this is where we're gonna start executing things. So initially, by default, we are in RE, but the trust is built from SMT and RE, because RE we don't trust at all. So we only boot RE when we are already correctly booted SM and T. Yeah, oh, actually I had the slides for it. So the system initially boots into the secure ward, then the normal ward boots from the secure ward. And then again, in order to switch to the secure ward, you need a privilege instruction. So it's not like every instruction can actually switch to the secure ward as well. Just keep in mind. And then there are APIs for remote attestation, secure code execution, and all those things. So if you, for example, use this trusted execution environment operating systems, there are SDKs for running, creating codes and all those things. So if you are an app developer, there are usually lots of SDKs and APIs for you to write the codes for all these things that I mentioned before. For example, for doing this process, there is SDKs and there are APIs that you use, okay, for loading and for checking and all those things. Okay. Questions? So the limitations of Trust Zone is that it has only two words, okay? So it's only RE and T. There is no problem. There is nothing that we can do inside each of these two environments. Another problem with trust zone is access to the IO is also very coarse grained, which means that either, for example, the secure ward or the normal ward can access to a particular IO, and then also within different applications within, for example, trust zone, all of them have access to the same same, for example, IO. As a result, if you remember, I told you that least privilege principle that we should always follow. Trust zone doesn't really, I mean, it's kind of follow it, but it's not the best solution ever, right? Because essentially we are saying that all the applications in the trusted domain, they all have similar access to the same things. For example, if this one application wants to access IO, now we are saying that essentially this application also has access to the same IO, which is unnecessary, right? So these are kind of like limitations of ARM trust. Okay. So in order to fix ARM trust zone, this is one of the papers that's kind of like look at how do we like kind of like improve ARM trust zone. It's called Sanctuary. It's essentially the idea is how we can you can add what they call user space enclaves. Okay. Let's have a quick break, then we'll come back and explain this paper to you. Okay. All right. So next few slides I'm borrowing from these guys. This paper is called Sanctuary Arming Trust on User Space Enclaves. So basically the idea is that, as I said, the questions that we want to achieve is, can I actually use ARM trust zone without really making big changes in hardware in order to achieve this kind of like mutual exclusivity between different user space enclaves? Okay. So this is kind of like this is what I showed you here, is that in commodity OS, we have a bunch of different applications. And one of them might be sensitive, right? And then we have the operating system, right? And then there is isolation between applications, obviously, because the operating system can't provide that isolation. But as long as the problem is that as long as the operating system works correctly, then we're good to go. But unfortunately, operating system itself is a large attack surface, very big, code base. So system can be compromised, and for example, if the one of the apps and the operating system are compromised, then the sensitive app is also compromised, right? This is kind of like what we discussed. And then the ARM trust zone model is basically fixing this problem by having this normal ward and secure ward, which the idea is that now you have your app and OS here, and now you have your sensitive app and your trusted OS on the other side. And now a good thing is that if, for example, this app and this OS is compromised, they will be blocked by this kind of isolation. Okay, this is so far what we have discussed. Okay, and then as I said, in order to kind of orchestrate between them, we usually have this thing called security monitor or trusted firmware. In this paper, they call it trusted firmware, but it's basically the same security monitor that we said before. Okay. But then we start talking about limitation of the ARM trust zone, right? And then the problem with limitation is that still, the system might be unnecessarily complex, because now we are saying that every single sensitive app and this trusted OS should be part of the TCB. Right. And then again, if somebody kind of writes a crappy app on the secure domain, that might compromise the entire thing, right? Because and again, attack here could compromise these other systems as well. Okay. So you kind of like, in order for this to work, you need to make sure that all the apps are bug free and so on, which is again going back to the original problem that we have. Okay. So what we should do is kind of like having something like this, okay? That if we can, for example, have some form of kind of like, normal word applications, but then provide these kind of like isolation correctly using this firmware, this security monitor, and some help from the secure ward, then we are kind of like having a much better system. Because if you're having the true isolation in the normal world or applications, this sensitive app is kind of like still a normal world, but we make sure that the trusted firmware and the secure world operating system helps us to make sure that these applications are secure. Then we kind of like have much better system. In that case, even if one of them is still buggy, as long as we kind of maintain this isolation between our apps, the system is secure. Alternatively, you can kind of think about this way, just to show you that, so alternatively, you can have something like this, that you have the normal and secure, you have your apps here, you have your operating system here, and then here you have your kind of like trusted OS, and then you have these apps, as I said. And then the idea here is that, can I actually kind of create isolation between these apps and these apps? In other words, can I kind of also make sure that this operating system is kind of can still maintain the security for these different applications as well. So kind of like having something like this. Okay, so this operating system service to this operating system service to this, and then we have the normal world operating system as well. Okay, so I want to create isolation between my secure apps. That's the goal here. All right, so how do we do that? And then, so this paper particularly, we're not interested in making big hardware changes, although you can actually make hardware changes as well. And there are lots of works after this work that kind of try to achieve this using hardware changes. And then they don't want to make big changes to the code base as well. This is kind of like their design goals, because they argue that this could make this system more applicable to larger systems, okay, better systems. But again, these are just some design constraints, okay? And the threat model that we're looking at was, the adversary can compromise all the normal world applications at all privilege levels. They can run malicious sensitive apps as well. As I said, like either the apps has some bugs that can be exploited, or someone can, intentionally create malicious apps. But the big thing is that we're assuming that if the trust zone OS is secure, then can we actually still have the system secure under control? Okay, so that's kind of the goal. And of course, most of these papers, they really don't consider physical attacks. So if you change hardware and change the kind of ordering of things, then none of these things will work. But this is just common in most of these papers, that they don't consider physical attacks. Okay. So they also kind of talked about, different related works, and this is actually good to go over it as well. First of all, there are software approaches for achieving this kind of secure world and normal world. We didn't really talk about this, but there's a whole bunch of things such as sandboxing and making sure that, systems like, software works in their own words. If you're interested to look at those, like take a look at these kind of papers here. Essentially just pure software-based solutions for achieving isolation. There are also methods based on virtualization of hardware, okay, that you can actually kind of not having trusted and secure, but like if you have hardware virtualization and have a hypervisor, you can also like achieve some form of isolation. And again, if you're interested, go and read this, but we're not interested in that. We're interested in systems that like single systems that have both trusted domain and normal world domain. And then, of course, you can change completely hardware. Again, some nice papers in this domain is a paper called Sanctum, which is kind of like this paper here. That's kind of like make big changes to the hardware. Again, if you're interested on the hardware side of things, take a look at this. We're probably going to talk about these kind of things in our next class, 209 class, next quarter. But here again, we're not really changing any hardware. Okay, so based on these things, let's see how this kind of multi-domain system works. So they're basically building on this fundamental observation that most of these devices, even IoT devices, have multiple cores. Okay, so they're Isolation will come from this fact that we can run various different things independently on different cores, okay? So for example, let's say you have core number one, you have a bunch of apps, okay? And now you have kind of your secure word application. And as I said here, you don't really run the apps on the secure word, but basically you have some kind of utility functions primitives here, okay? And then your memory obviously will be divided into normal word and secure word for this, okay? This is the classic trusted. What these guys are adding is basically saying that let's have other cores, and now let's run our sensitive applications on those cores, okay? And then what will happen is that, for example, we call this Sanctuary 1, and I can run my sensitive application here, okay? And again, here I'm going to have its own kind of security primitives, and it's going to have its own memory boundaries, okay? And then I can continue in doing that. So let's say I have two sensitive applications. As long as I have cores, let's say, for example, this is a 4-core system, I can run, for example, 4 sensitive applications all at the same time, or like 3 sensitive applications and 1 normal application, whatever it is. The nice thing is that this can be kind of like, achieved using this course. The reason for this is basically the way that, Trustzone works, and I'm going to explain this in next few slides. But just before that, kind of like, the benefit of this is that it doesn't really use any sort of hardware changes. It's still using the same trust zone, fundamentally using the same trust zone. It's just using the fact that physical cores are physically separate, and they're kind of managed, the memory managed for each core is physically separate. So you can actually build on top of that to have this physical isolation between apps, okay? So that's kind of the idea that they're going after. So the details is basically this, like the fundamental things, the reasons that this works is this, okay? So let's say you have 2 cores, core 1 and core 2. Then you will, as if you remember, I told you that all Trustzone does is just 1 bit of secure versus normal, okay? So if the request that comes is 0, is usually normal word. If it's 1, then it's secure word, okay? And that's why the memory controller will kind of understand where the request is coming from, okay? So this is basically the classic non-secure, okay? But what we can add on top of it is essentially this non-secure access ID that actually Trustzone also supports for multiple cores. And then what this does is basically saying that, for example, your sensitive app is in core B and is insecure. So your NSID, access ID, for example, is equal to 1, and then your secure monitor is also equal to 1. This means that this is the app that we are looking at. If NSID was equal to 0, then this is just a regular app that we are accessing from core 0 and so on. So this way we can then have physical isolations among this different, as long as we have different NSIDs, then I can basically provide this fine-grained level of isolations between different applications, okay? So this is kind of like on top of this SM, I'm also having this, non-secure access ID kind of. Okay, very simple, very straightforward. Questions? Yeah.
Yeah, I'm sorry, it may not fit this slide, the question, but the idea is that if I, as an attacker, gained access to the normal world, would it be possible for me to take one of those apps and move it into the secure environment or enclave, or is like who gets control, who decides?
So yeah, I think back somewhere I mentioned that switching to the secure world require privileged access, okay? So you need to be privileged, you have to have privileged access to be able, but if you have, then you can switch. So for example, there are attacks that kind of they self-promote them to the secure world. That's totally possible. But again, the assumption is that at the user level, nobody can access the secure, nobody can, promote themselves to the secure world. But there are attacks, for example, fault attacks are very interesting because, for example, if deciding whether you're secure or normal is just 1 bit, if I can flip that bit somehow, then I all of a sudden I become secure, right? So this is kind of like the basic idea.
Basically, the attacker has gained root access to the system.
Yeah, if you have root access, but then if you have root access, you can do other things as well. So
thank you.
All right, and then essentially your memory will look like something like this. You will have your normal core A, you might have normal word core B, you will have secure word, and so on and so forth. Okay. And yeah, and then you can just continue doing this, right? So you have the second core here, like the third core here, like the sanctuary core. Then you will have all your sensitive apps here. And then basically what will happen is that you will have a specific, say, like sanctuary memory, area for this sensitive app. And again, as long as this NSIDs are different, so for example, this one is B and this one is C, then this app cannot access this blue part, and then this blue part cannot access, for example, this white part, and so on and so forth. Okay, and as long as I have the more cores, I can keep doing this, right? And as I said, this is just mainly just the management part. And this, the nice thing about this is that this part no longer needs to be part of TCB, right? So the app itself does not need to be part of TCB. So if somebody writes a crappy app, the only thing that happens is that this part is going to get, change. But you're not going to mess up your secure word or other sensitive apps in the system. So that's the big difference between the regular trust zone and the sanctuary-based trust. Okay. They also kind of evaluated, so kind of like protection against compromised OS, protection against malicious sensitive apps. And then these guys also look into the side channels. Well, you don't need to worry about this. So important things about, as I said, about generally any sort of trusted execution environment app is that there is this additional overhead that comes for switching between normal board and secure board, and for creating and distracting an enclave. Okay, so usually, if, for example, your regular operating system is executing, the moment that you want to create a new enclave, then you will kind of you will have to create a new enclave. And remember, those like sending the key, receiving the key, doing the attestation, encrypting, decrypting, all this part of the initialization phase. Okay, so this part here is kind of like extra overhead that you're paying the first time you're creating an enclave. Okay, then you will start executing the enclave. For example, this is the sensitive app execution. And then, for example, if you have multiple cores, then you can run things in parallel, right? So your operating system can run in parallel with your sensitive app execution. But if you can also here, you can context switch between the normal and secure apps, that's also fine. And then once you're done, you also need to do destruction or tear down of the app. Again, here you need to kind of send the result, like encrypt the results and send the final response. And then you need to kind of sanitize the memory from all the secrets. So there's also additional kind of overhead that's happening here as well. And then you go back to the normal execution. Okay, so this is kind of like these two red parts are kind of additional overhead that you're paying on top of what you would normally use in order to run apps. Okay, so yeah, then this is kind of like the numbers that you're sharing here. Code modifications. It's kind of like to show that it's not a big deal, like in terms of changing parts. And yeah, I don't think I have the kind of the results for the time, but generally, they show that this additional time is negligible compared, like as long as your sensitive app runs for enough time, then the overhead's not going to be huge. Okay. All right, so that's kind of it for Sanctuary. Does not introduce new hardware, but allows the system to be kind of shared among multiple apps. Any questions so far?
Didn't the memory controller have to change though?
No, so the question is like, does the memory controller needs to be changed? No. So what they found is that actually so this is their main observation, that this NSID already exists in existing trust zone implementations. So they didn't change that. So the only thing is that they show that, you can actually leverage this for trusted execution environments.
No. If
But yeah, if you didn't have that, then of course. Any other questions? All right, so I want to talk about kind of like a expanded version of this sanctuary, and this is called Cure. This is actually kind of like, again, from the same group of people. And the idea here is that, you can have a customizable system so that if you want to have just 2 wards, you can. If you want to have multiple wards, you can. If you want to have like multiple wards, some of them simple and some of them more complex, you can. So generally the idea of this is that we can actually make T's very, very customizable. Okay, that's why they call it Cure or customizable T's. Okay, so again, going back to the idea, this is kind of like where we have now that we have the operating system, normal ward and secure ward, and then, as I said, we usually have something like this where, the operating system is considered compromised, but we have some form of a trusted software that kind of controls everything and make sure that the enclaves are running securely. And then in terms of resources, you're kind of secure because you're kind of making sure that there is boundaries and there's isolation between different units. Okay. And usually this trusted software is the one that's managing all these things, right? So this is so far what we learned. Let's actually kind of like review what are the different types of enclaves that we can have. So usually, for example, this is a regular system that we have. We have a bunch of different apps. We have the operating system. We have our memory system. Let's say, for example, we have the cache. We have the memory management unit. We have the translation look-aside buffers or TLBs, which is for just managing the pages. And then we can have like things like L2 cache, and then we can have our DRAM, right? So this is usually what we have. And then this is the user level. This is a privilege level, right? This is a regular system. Then you can have like various different enclave and then a trusted software. And as I said, you can like kind of like, manage your system this way. That different enclaves have different access in the memory, and this is what they call user space enclave. Essentially, the idea is that you have only enclaves at the user space, and we really don't change the operating system and all so much. The problem is, as I said, if this is compromised, the entire system will be compromised as well, which we didn't like. Okay, so what you can have instead is kind of having this separate enclave and runtime environments together, right? So you can have one enclave, and the difference between kind of kernel space enclave and user space enclave is that now the runtime environment comes with the enclave itself, so there's an isolation with the system, and so on and so forth. The pros and cons of this compared to the other is, so first of all, the pros is that the code runs in the enclave. There's no overhead on the context switch because essentially everything is kind of self-contained. And then what the cons is that the resources are much more because now every enclave needs its own operating system, right? And then the setup and teardown is also significantly higher because now every time I want to create an enclave, I need to also like boot a new operating system with it. And then the runtime development is also significantly higher, okay? Because essentially now I need to also come up with design of my enclave, okay? And then the idea of customizable is that essentially we can have both like all of these different flavors, right? So I can have user space enclave, I can have kernel space enclave, and then I can have enclaves that they have their own separate kind of users, like they have their own separate memory system, okay? And then basically this SM needs to kind of manage all of these different things, okay? This is where kind of like all these services needs to be managed, okay? That's a big difference between them. And then the nice thing about this is that now you can even have you can extend this to the peripherals and to the memory as well. So basically, they introducing this what they call filter engine, that based on this, like which enclave is trying to access this, the peripherals also can be considered as kind of a unified version of the memory. So now, for example, C can access this, like, this display, versus now, for example, this enclave can access these yellow ones. Okay, so the Wi-Fi and the camera and so on and so forth. Okay, so the system bus, if you actually further extend the system bus, then we can have access to these things as well. Okay. So how do we do that? They kind of provide some details. I'm not going to go through the basics of it, but this is basically another protocol for I/O called tiling. This is specific for RISC-V based architectures. Again, this is just the protocol for connecting this. So, for example, we have a bunch of different cores, and then this is the system bus here, this white one. And then this is, let's say, this is the peripherals that we're trying to access. What they do is that they show that, one can have a bunch of these different address and masks. And this mask will allow, for example, to say who is accessing to what. Okay, so essentially, they kind of like, enforce this access policy to these different enclaves. And this mask, as long as this mask can be updated when you're creating an enclave and removing an enclave, then you're good to go to kind of accessing these different peripherals. Okay, questions? But this one does indeed involve hardware changes. So these things are not default in most of the systems. So you actually need to make these changes. The software components, what's out there. So you have our operating systems, you have our runtime, and you have our regular apps and enclave apps. Again, the difference between them is that the runtime is the ones that kind of provide kind of simple, functionality to this enclave, but still most of the things are run in this SM, this security monitor. So things such as intro configuration, memory communication, and all those things all happens on the security monitor. Okay. And then, yeah, they talked about, various different things. For example, this could be a Linux kernel, this runtime environment. This also could be a Linux kernel, but like, a bigger version. And this is usually the simple things such as, some crypto functionality and so on and so forth. Let me see. So I think I talked about these things. Yeah, and this is basically just, as I said, the goal here was to show you that, there are various flavors of enclaves, and then you can have mix and match various different things. You can have, user level different applications that they share the same entities, shared operating system. You can have each application have their own operating system. You can, make them isolated from each other, but without having an operating system, so they can have all these different options when you're building an enclave. So this is kind of like what we have state of the art in terms of enclaves. Questions? How are we doing with time? Okay. So other examples. There are a whole bunch of other examples. I have actually two more, which I might actually pause for now. Like I might talk about one of them and then do the other next time. We're actually going to see a lot of a few examples in your paper presentations on Wednesday as well. But generally, things to consider when we are talking about trusted execution environments is what sort of operating system are we using? So, example, are we using a full-on operating system? Are we using a real-time operating system or a runtime environment, or are we not using an operating system at all? There's actually also some form of trusted execution environment for like bare metal systems that we're going to actually talk a little bit about. The second question is the multi-tenancy, right? So do we want to run multiple, applications at the same time? Is it going to be switched between them? And then what sort of hardware resources do we have? Can we change hardware or not? What sort of flexibility do we need to have? And of course, the big thing is the I/O and access to the, input and outputs. And as I said, you're going to see more of these examples in in the paper presentations. Okay, questions? So this is actually one of the papers that are going to be discussed on Wednesday, I think. So I'm going to skip this for now. I'm going to come back to this when you're talking about this. This is basically to just give you a high level overview. The idea of this paper called Pistis is can I have like a memory controller and have some form of memory isolation for various different applications on this system? Can I have some form of trusted execution environment for memory controller units or MCU? The difference is that here I don't have any sort of operating system in the system. So all these managements of R and T's and C and things like that, there's nothing there. So there's kind of like, you have to be innovative of like what you can do. The main idea that these guys came up with is that you can actually have, again, some form of memory isolation at the hardware level and kind of like run some code, like develop some runtime library, some small code that they call Pistis Trusted Computing Base. This is basically provide the minimal amount of trust that requires for having a T. So they have things such as remote attestation, secure update, and so on and so forth. And then the rest of the applications can just sit regularly on the MCU, and they show that with this kind of design approach they can have, they can achieve some form of trusted execution environment guarantees. And then you need to kind of like change the code slightly to make sure that the system works. I'll let your classmates kind of like explain this when they're explaining it on Wednesday. And then in order to make sure that this system works, they need to also reconfigure their software. For example, they need to make sure that there are safe calls and function calls and so on and so forth. So you need to actually change the binary a little bit. So that's one issue with Pistis, that you actually cannot like run regular codes normally. This will result in some form of increase in memory footprint and runtime overheads around 40 and 50%. But the nice thing is that the system would be completely secure against these type of attacks. So yeah, that's it with the Pistis. But the reason that I kind of didn't go through the details is that I want you to kind of wait for Wednesday, so that you see the presentation, and then come back to this and explain this. Let me actually jump over this, and I'm going to come back to this on Wednesday because we have some time. Let me just finish this with another thing that I want to discuss as well, and then this part I can come back and talk about it on Wednesday. So if you remember last week, we talked about kind of things that we want to do, right? So we talked about dynamic status checking. We talk about isolating various parts. When we talk about checking the integrity of the control flow. This dynamic static, we talked about this as a remote attestation. This isolating different parts, this is basically what we talked about T's. This part in the middle, kind of checking the integrity of control flow, we kind of talked about it a little bit when we were talking about control flow integrity, like saying that, okay, these are the possible ways that you can do. Another way that you can do this is based on what we call runtime attestation. That is, like if something happens and then you follow some path, can I still check whether this path was a legitimate path in this program or not? In other words, I'm trying to find that, if there is some form of return-oriented programming or data-only attacks, can I find that there is some violation? Okay, this goes under the umbrella of what we call control flow attestation. So instead of like doing memory attestation, this is what we learned so far. We are trying to see whether that control flow that we followed is the same things that we expected to happen, right? So how do we do that? First of all, T doesn't help here. Again, here we are trying to kind of fix the issue within one application. Okay, we are trying to fix the issue of similar memory corruption attack, control flow hijacking attacks that we talked about before. Okay, so this is what we call kind of runtime attestation. Again, if you remember, the problem with this was that, you know, some input will result into the code to jump to some part of the program that it wasn't supposed to, right? And we are trying to kind of detect this, okay? So for example, if you look at the CFI, you're now expert in CFI, you know that, for example, the CFI was like, you know, from block 1, you can go to 2 and 3, and from 3, you can go to the 4, and from 2, you can go to the 4. But for example, you cannot go from 2 to 3, okay? So this is an unseen or impossible control flow, okay? So the idea here is that if I run this code with a bunch of different inputs, I'm going to gather some control flows. So for example, I'm going to see 1, 2, 4, maybe another 1, 2, 4, maybe sometimes 1, 3, 4, and so on. But if I see 1, 2, 3, or if I see 1, 2, I don't know, like some other number, this means that there is an obvious violation of this thing, which indicates that there is an attack, okay? So the idea of control flow attestation is that, can I detect these kind of violations? Can I check these and say that, okay, when I see this, I say that, oh, this is okay. But when I see this, say, oh, this is an attack. How can I do that? And this is a very, very similar way of doing this to what we did for remote attestation, generally memory attestation. We compute a hash, okay? And we know, so basically, once we are kind of like following the control flow, we compute the hash, we update the hash, okay? And then we send the final hash to the remote user. The remote user knows all the possible, you know, options of a hash. They're gonna see that, okay, whether that hash is an acceptable hash or not. Okay, that's kind of like the simple idea. The big difference between memory attestation and control flow attestation is that for memory attestation, there was just only one acceptable response. For control flow, there might be many, because there might be different possible legitimate path in the program. So the verifier needs to kind of store a large number of possible paths in a program. Okay. The second problem in this control flow is the second problem is the issue of kind of loops and backward edges, because, you know, backward edges needs to kind of like, you know, creates lots of these problems with the control flow. So we need to kind of fix an issue, because, for example, let's say if I want to compute a hash of this basic block, every time that I iterate over the loop, the hash, I need to recompute the hash. And I need to do it over and over and over. And the problem is that my final hash would be a function of number of iterations of this loop. And then if this number of iterations is changing, then my hash would be very different. So I might have the infinite number of hashes just because the number of iterations of my loops changes, okay? So I need to get rid of these kind of problems in control flow attestation. I need to get rid of loops. And then understand that this is a loop. I calculate this before and do not update my hash every time I see a loop, okay? So this is kind of also a unique problem. Again, this is one of the papers I think is going to be presented on Wednesday. So I'm not going to go through the details of this. They're going to, your classmate's going to help you with understanding the details of this, okay? And then this is kind of like, you know, if you think about how this is implemented, usually you can use T's to implement this control flow attestation. So essentially your kind of hashing function is on the T side, your regular application is on the normal word, and whenever there is like something that you need to kind of quickly update, you switch between your normal word and secure word, you use that, you know, you kind of use your hash engine to update, and then you go back to the normal word. And again, I'll let them to explain the details of this as well for you. All right. This control flow attestation is actually quite interesting. There are lots of works that came after this. This originally was presented and proposed in 2017, but afterwards there were like a bunch of papers, things such as like, what's the better way to aggregate the measurements? Is there a faster or simpler way to do the hashing? Can I have like a hardware support for this rather than just using like trusted execution environments and so on? So there are a whole bunch of papers that came after this original papers that kind of look at these different problems. If you're interested, definitely go and take a look. So yeah, I think that's pretty much it for the T part. There's like those two papers that I need to describe. I'm going to describe it on Wednesday. And then we're going to have the paper presentations on Wednesday as well. Any questions? All right, so let me also then quickly go over the project one more time because there were questions. So the goal of the project is, first of all, you need to create an attestation mechanism, right? And the second part is you need to create an attack. And the third part of the project is that you kind of wants to see if there is any defense that is applicable to the system. So it's kind of like there are three phases to your project, right? The first phase, I think, is pretty straightforward. You just need to kind of like compute a hash using a hash library. But you need to do it line by line because when you're designing your attacks, you have to design your attack line by line. So instead of like fitting the entire folder to a hash function and getting a hash function, is better to do it in a for loop kind of things. So that's, I think, the first parts. I think the 1 to 3, I think is something like that. It's just for this. The main part is this attack part. You have to think about how do you basically circumvent this checking mechanism, okay? So think about it from an attacker's perspective. Think that how do I have, so you have like, the file that you have is this attack file, right? That is obviously different than the original file, okay? So you're assuming that, and then by the way, files are proxy of the memory. So instead of like having memory, we are dealing with files, okay? So the idea is that the attacker has modified the memory. That's why their content of the memory, which is their files, is different than the original files, okay? But now the question is that once the attestation comes, can I compute the hash, okay, based on the content of the previous file, okay? So one obvious thing is that you just open the previous file and do it. That's not what we're looking for. We're trying to mimic a real-time attack, right? So the real-time attack, the assumption is that you kind of store the correct content as like a lower half or upper half, and you need to kind of constantly redirect the memory accesses to the other parts of the memory, right? So we are basically asking you that can you first prepare this file such that half of it is your kind of attack and half of it is the correct content, right? This is the first part you need to do. The second part is that you need to constantly redirect the accesses. So when you were computing a hash, instead of computing the hash from this kind of modified version, you need to kind of change the address and goes to the bottom of this file and then read it from there, right? So eventually in this attack, you want to fool the checker. You want to fool the checker such that you create a hash that is same as the previous hash. The exact details is your job to figure out, right? So kind of like being vague so that you can actually think about how do I kind of like forward this and so on and so forth. Yeah.
So the file, the original file has like 1600 entries.
Mhm.
Whereas if we do the modified one, that will have like only 800 entries. So the 1600 one, the rest of 800 are zeros. So we
Mhm.
have to somehow obtain those zeros also to, or do we ignore those zeros?
Well, that's another part, right? So assuming that you know the half of the file is all zeros, then you don't need to append, right? You can just substitute the zeros with the old file, and then whenever you reach to the half, then from the rest you just assume you don't read the files. You always kind of forward zeros, right? So that's what you should do. Okay, so there you need to kind of come up with a dynamic mechanism that eventually create the same hash file than the original hash file. That's the goal of this basically part of the code. And hopefully once you did that, you'll see that your code basically passed the hash function test, obviously. And the last part is that seeing that whether some form of software-based detection mechanism can help us. Yeah, question.
So I talked to you previously about
Mhm.
how my attack and my normal attestation
Mhm.
are pretty much equivalent.
Mhm.
And so what do I do in that situation?
So first of all, you have to see how do you implement that, right? So I mean, if you're doing this, so so for example, one thing you could do is that in real system, you kind of like need to kind of redirect this, okay? And then each redirection has some time overhead, okay? In your system, depending on how you implement this attacks, this redirection might not have any delays or might have very minimal delays. You can do things to artificially kind of increase this delay. For example, instead of like, keeping the file open, you can try to see if I open the file every time that I want to access, what will happen, right? So this obviously creates a huge amount of delays. And that would be something that you can see. Here, I'm not really trying to kind of force you to see the difference. I'm just curious to see, depending on the implementation, do you see the difference? But you can actually write your code such that it will create a huge difference. If you, every time you open and close the file for every redirection, then that will be a huge time difference for your normal and does that make sense? But yeah, so for the defense, continuing what we said, the idea is that if I time this, whether there will be a noticeable time difference between my attack and defense. It may not, but as I said, you can actually modify your code such that it may, right? So the idea is that I want you to see that, for different implementations, there might be different ways of doing this. And lastly, you can actually add some noise to see that at some point, at what point these two becomes similar to each other, right? Because that's basically the problem with software attestation. Because in software attestation, the channel is noisy, the communication is noisy. For us, the communication is not noisy, it's perfect. But with adding this noise, you make this communication also noisy.
The noise will be added to both the systems.
Up to both systems, yeah. So in other words, your baseline is no longer like a small number. It could be like the baseline goes up, your attacks also might goes up and down. Any questions? Yeah.
So it says that when we're creating the nonce, we need to make sure that it doesn't repeat if you're doing multiple attestations. When you're saying like multiple attestations, does that mean like attestation of like the first line and the second line?
No. So each time you do the full,
Oh,
memory is one attestation. But I think somewhere I said that repeated like 10 times or so in order to time it. So that 10 times, each time you do it, you have to generally create a new nonce.
right. Just double checking. So each time you will generate a new random number, like the nonce.
Yeah.
It's like they're independent, right? So then like hypothetically, it could be the same number.
So that's why your code should kind of remember what nonce it creates, right?
Oh, so it will be like without replacement then?
Say it again.
So sample a random number without replacement?
Yeah, or you can have like a database of existing nonces. You query your sample random number, you kind of like check it with the existing numbers and see if it's there or not.
Got it. So does that like just because I want to get this right, does that mean that if I perform 257 attestations?
You will have a repeated nonce, yes. But this is like a very small nonce, right? In reality, the nonces will be 32 bits, so 2 to the power of 32 possible nonces. But here you just need to do it like 10 times, like 20 times or
But
something.
if I do like 257 attestations, I will have an overlap.
You will have an overlap for sure. Yeah. In this particular case, yes. Yeah. We're good? Any other questions? All right. See you guys on Wednesday.